Hello there, ladies and gentlemen. Welcome to another exciting edition of HL Chemistry for the Classroom. This is Mr. Los. Good to see you again, although I'm not really seeing you. And let's just get started. We're going to be talking about something called voltaic cells today, otherwise known as galvanic cells. Those terms are used interchangeably. But before we start talking about them, I don't think you need to write the stuff on this slide down, but this is just a little kind of something to think about to help us get started. Here we have the classic single replacement reaction where we have a piece of zinc metal dipped into a solution of copper 2 sulfate, and there's a redox reaction taking place where the zinc, this actual piece of zinc metal itself, the atoms in the zinc, are losing electrons, so they're being oxidized, and then the Cu+2 ions that are in solution are getting reduced and going back to elemental copper. And we've talked about how this all works in general. So the thing is, if you take a look at this reaction, it's exothermic. So if you felt the beaker, it would increase in temperature while this reaction is taking place. It releases free energy. So is there some way that we could take this reaction and we could harness the energy in this reaction and do something useful with it? And yes, there is. We can harness this energy by constructing something called a galvanic cell or voltaic cell, and this is the basis for all battery technology. And obviously, with the way the world is now, with devices and electric cars and all that kind of thing, battery technology is some of the most important and most critical stuff to the future going forward. So again, what we're talking about basically is batteries. This is the basis of how they work, is voltaic cells or galvanic cells. So stepping back for a second, and this is the part where the note starts, so this is the part that you should write down. Electrochemical cells in general we're going to define them as useful devices based on redox processes. And there's two big types. The first type is the one that we're going to be talking about initially here, which is galvanic cells or voltaic cells, which use spontaneous reactions. Remember, spontaneous meaning the reaction happens without constant energy input to generate electricity, generate electrical energy. The other big type of cells are electrolytic cells, which are actually non-spontaneous reactions. So if you remember, non-spontaneous reactions require constant energy input to happen, and so they actually require electricity to run. And you may wonder, what is that useful for? Well, we're going to talk about it, but just quickly, things like metal plating or getting metal out of rocks, out of ores, like how we get aluminum is from an electrochemical cell, and various other metals, an electrolytic cell. So that's going to be down the line. The first one, and the one we're going to talk about today, is voltaic cells. So the spontaneous reactions, these are the things that produce energy as they're running. Voltaic cells are split into two half cells. Oxidation happens in one half cell and reduction in another. So basically, you're taking that reaction and showed it you on the first slide, and you're splitting it up. And electrons are going to move from one cell to another due to a difference in electric potential, which we're going to talk about later. But it's related to like the activity series and things like that we've spoken about. There's going to be a force that's going to drive electrons from one cell to the next. So here we have a little schematic or an example of a type of galvanic cell. So the whole thing is a galvanic cell. These are half cells. The conductive solids, these things are called electrodes. So there's an electrode in each cell of some kind. And the electrode where oxidation is taking place, or really it should say the cell where oxidation is taking place, is called the anode. In a voltaic cell, this is considered the negative electrode. And then the electrode where reduction takes place is called the cathode, or cathode, I'm sorry. That's considered the positive electrode. Now, we've spoken about some of the confusing terminology, and there's a lot of it. Even more in this section, anode, cathode, all that stuff. There is some mnemonics we'll talk about later to help you sort through and remember these things, but it does get a little confusing. And like I said, I've already mentioned the confusing terminology in this unit. So in this case, this is the anode, this is the cathode, oxidation's happening here, reduction's happening here. So again, it's that same reaction I showed you on the first slide, except instead of the zinc being dipped directly into the copper, it's in its own separate cell. So we're going to force the electrons, instead of just directly transferring to the copper ions, we're going to force those electrons to travel over this wire. And then if they're moving through the wire, we can do stuff with those electrons like power something, run a little light bulb or whatever we're going to do with the electricity. So we're kind of forcing electrons to take a path that we want, and then we can use the electrons to power stuff. That's what electricity is, a flow of electrons. So typically the way you're going to, and you do need to know how to build galvanic cells, basic galvanic cells. Electrodes typically are going to be metal strips placed into a solution of their own ions. So a zinc electrode in zinc ions, for instance, or a copper ion in copper electrode. That's at least for the simple kind of galvanic cells, that's what you're going to want to do. What you do not want happening is an actual chemical reaction taking place within the half cell. We want these electrons to go over this wire and go over here. We don't want any electron redox happening in this thing. We don't want any precipitates forming or anything like that. So the best way to ensure that a metal is not going to react is if it's in a solution of its own ions, that it's not going to react with those. You also, well, I'll get to that in a second. Sometimes the electrode itself is not actually reacting, and in that case you could use a graphite or platinum electrode. Sometimes, depending on what's going on, you might have to use a graphite or platinum electrode. We'll talk about that. But like for example, in this case, this actual piece of copper metal here is not reacting. Remember, we've talked about this big distinction. It's actually the Cu+2 ions that are getting reduced. It's not the copper. So you could replace this electrode with a stick of graphite, for instance, and this would still function. The anode you could not. This actual anode is reacting and releasing zinc ions into solution. So we do need this piece of zinc right here. This one could be replaced with a piece of copper or platinum. Platinum or graphite. Anything that won't react with the copper solution here, because again, we don't want that happening. So how you would actually, if you had to go about it making this is a solution. You need to make a solution. You can't just like get a bottle of zinc ions, right? You need to have some kind of ionic compound that contains zinc ions. So the best thing to have would be zinc nitrate, because zinc nitrate contains Zn+2, and then copper nitrate. Use those ionic solids, make a solution out of those ionic solids, and that's what you can fill your half cell with. The reason why nitrates work well is they don't form precipitates with anything. And so we don't want other like carbonate or other anions that tend to form precipitates. We don't want those in there because we don't want any kind of reaction taking place except the one that we want to have happen. Chlorides are pretty good, so you could use zinc chloride, you could use copper chloride. The problem is, though, in some cases chlorides are going to form precipitates, like with silver, for example, and a couple other things. So nitrates are guaranteed to get no reaction. That would be the ideal choice. And then again, we're going to force only this one reaction to take place that we want taking place. So electrons, we need to kind of know what's happening with the charges and where they're going. Electrons travel from anode to cathode. That's where they start. They start at the anode, they go to the cathode, and they travel through the wires. That's how they get there. Voltaic cells require a salt bridge. That's this thing right here. And electrons do not travel across those. What travels across those are the ions, the positive and negative ions, the cations and the anions. So anions, which are the negative ones, and by the way, this salt bridge has to be there. You can think of it like it completes the circuit. If the salt bridge is not there, this cell does not function. The reason it doesn't function is, let's say a couple of electrons travel over here into this cell. If there was no salt bridge, this cell would have a net negative charge, and then no more electrons would want to go across over to the other side to try to push their way into that negatively charged half cell. What the salt bridge allows, it allows charge to stay balanced. So every time some negativeness goes over here, a couple of positive ions will go in to sort of cancel that out. And again, it kind of completes the circuit. So electrons are traveling through wires. The ions in solution are traveling through the salt bridge. So anions, as the cell runs, will migrate towards the anode, which is the negative ion, and the cations, which are positive ions, will travel towards the cathode. Now, if you are really on your toes, you might be thinking, that doesn't make any sense. You said the anode is the negatively charged electrode. Anodes are negative ions, so why would negative ions be drifting towards this electrode? Because like charges repel, right? So wouldn't you expect the negative ions to go towards the positive electrode? And it is dependent on perspective and how and why we called this the negative electrode. So think about it like this. If you were a little person, a little dude, if you were in this wire right here, and you were, that's you're like a little person living in this wire. From your point of view in that wire, electrons are coming in this direction and going in this direction. So from your point of view here, this seems like it's negative, and electrons are going towards this, which is positive. And because of the fact that in a galvanic cell, we're interested in what's going on in the wire, we're going to somewhat arbitrarily call this the negative electrode and this the positive electrode. On the other hand, though, from the point of view of the solution, if your little sister was living in the solution here, and so from, I don't know why that cracks me up, but so from the point of view of someone living in the solution, look at what's happening here. What happens is these zinc atoms lose electrons, and they are constantly spitting out Zn+2 ions. So from the perspective of this solution, there's constant positiveness being generated there. So yes, if you're an ion in a solution and you're a negative ion and anion, you're going to be attracted to the anode. And just the opposite, if you're in this solution, if your cousin, this is your sister, if your cousin lives over here in this one, then since this is the constant source of electrons, positive ions in solution are going to be attracted to this electrode over here. So electrons travel from anode to cathode over the wire. Ions in solution travel over the salt bridge. You need both the salt bridge and the wire, or nothing happens. The cell does not run. What is the salt bridge? Well, traditionally what it is just kind of a tube with some kind of absorbent porous material in it, and you need some kind of electricity conducting compound in it to get things going. For some of the same logic we talked about before, you want something that's quite unreactive, like sodium nitrate is a great choice. That reacts with sodium ions and nitrate ions are super stable and react with almost nothing. So they would be a good choice. You could use an ACl. Again, that's going to form precipitates with a few other things. It just needs to be something conductive. It can even be a strip of like paper toweling, a paper towel strip, really. It could be as simple as that, depending on exactly what kind of voltaic cell you're going to build, as long as you soak the paper towel with like an ACl or something aqueous. So a couple of ways to help remember here, because again this technology is rather confusing. You got electrons flowing from anode to cathode, so that's fat cat, from anode to cathode, like that guy right there. I think that might be photoshopped. But, yeah, electrons flow from anode to cathode, and we could say fat cat to help remember that. And then there's another saying, CPR, like if you give someone CPR, life-saving CPR, that stands for cathode reduction positive. So if you remember CPR and you remember cathode reduction positive, well then the anode must be the place where oxidation takes place and is negative. So if you can remember what the cathode is doing by saying CPR, you must remember that the anode is just going to be the opposite of all those things. Now the little trick is that in an electrolytic cell, some of these things work a little differently. I talked about the other major kind of cells, so that just adds to the confusion. But these things definitely work for a galvanic cell or a voltaic cell. Fat cat, electrons flow from anode to cathode, and CPR, cathode reduction positive. And of course, we'll be going back over all this stuff in class and practicing. So one last thing I'm going to mention here. There is kind of a shorthand way of diagramming out what is in a cell and what it's constructed of. You write it from left to right, anode to cathode. A single line is used for things that are in a different phase. Typically that's going to be from the electrode and the ions in solution is where there's going to be a different phase. And If there's more than one ion in the electrolyte solution that are not spectator ions, like multiple ions that actually are part of the chemical reaction, you would separate them by a comma. But for instance, in this cell right here that you see on the right side of the screen, a shorthand way of diagramming what that would be like. Oh, and the double line is the salt bridge, by the way. So the shorthand notation that would describe that cell on the previous screen is zinc, because it's a solid zinc electrode, and then you make a single line, and there's zinc ions in solution. This represents the salt bridge, and then we have the copper ions in solution. Phase boundary, we have the solid copper electrode. So you kind of go from left to right. You go from the anode, the actual electrode of the anode, all the way over here, and yeah, it ends up looking like that. So that's all we need to talk about for right now. Thank you for watching, ladies and gentlemen, and have a great evening.